Okay, AP Physics C. A little more on that position-dependent force. All right? And I always like to start off by talking about gravity here. All right, gravity. So we looked at it from, the basic perspective. So it starts up here, right? Some height, h, right? It ends down here at height. Let's say it's y equals h, y1, y2 equals 0. All right, and the force pulling it down, all right, I'm essentially saying down is negative the way I made this, right? So the force is negative mg. So if we look at the very most generic definition of work, all right, I'm trying to get a little better light on our videos here. Work is equal to the integral of force with respect to position. All right, and technically there's dots here. Now, whenever you're using this integral in this course, it's going to be one-dimensional motion. If a one-dimensional motion, the straight line motion, straight line force, no angles, this is just going to be force and whatever direction you're moving in. We ignore the dot for the most part. All right, so the work done by gravity on the object over this motion is equal to the integral. Now this is the thing, initial to final, so it's actually from h to 0 because it's going down, right? H to 0 if I drop it, gravity, the force. And the force is negative mg. And we got to integrate it over, believe it or not, in this case, it'd be your displacement direction would be dy, the vertical direction. All right, so this is just a constant, right? So that comes out in front, h to 0, negative mg out in front, dy. Well, that's like a 1 right there. So the integral of just 1 is negative mgy evaluated from h to 0. And look what you get. You plug in the top. All right, so I get negative mg times 0. Plug in the bottom, but you subtract that, right? So it's minus mgh. This goes to 0, you get mgh for the work done. Pretty cool, right? So the work done on that ends up being mgh. That's pretty fun. Work done, and this is calculating the work done on the object. A similar question that we already know something about is if we look at force. Now I really should get a whiteboard here. I'm kind of burning through paper, but I've been saving these, stacking them up. If we look at a spring force, right? All right, so let's say, I don't know, let's say we have a flat spring. Oh, I don't know. Let's say the spring is stretched. All right, and this was its equilibrium position, 0. Let's say it's stretched over here. All right, we'll say it's at a location of positive x. All right, it's been stretched and we're going to let it go. So this is the initial situation. Now I want to figure out when it gets to its equilibrium position, all right, what's its kinetic energy? Okay, so this is the object. Now here's the thing. The force here of spring force, right, it's always opposite the direction that it's been expanded in. So in this case, the force is this way, right? This is the spring force, right? So again, I've basically said this is the negative direction to the left by saying I've moved it to positive x. So the spring force here is negative k times x. And x is our variable for let's call us x max to give it a name here. All right, so that's our spring force. We're going to let it go. It's going to get kinetic energy when it gets to here. let's figure out how much kinetic energy it has when it gets there. So the work done by the spring on the object is the integral of from positive x max, and we're going to go to 0, right, because we're starting there. You're literally initial position to final position, initial position to final position. We want to find the kinetic energy here, basically, is what we're looking for. And remember the work energy theorem, the work done equals a change in kinetic energy. And also it equals a negative change in potential energy. All right, equals work done equals negative delta US. All right, so we're just going to prove that though. And the variable which we integrate over in this case is dx. Yes, that same x. All right. And the force is negative here. Negative. It's always got to be, you always have to put that negative sign there, because depending on what your x is, that's going to make that negative. So the spring force, this is why we make it negative, because it's always going to be opposite direction of what x is. So if x is, if we started over here at compressed, right? So our bounds would be negative x max to 0, while the double negative would come into play there. So we take the integral of that function, negative kx, so it becomes negative kx squared over 2, evaluated from positive x max to 0. All right, so we evaluate, we plug in 0 first. Negative k times 0 squared over 2. All right. We subtract off what we get when we plug in the bottom bound. So negative k x max squared over 2. Usually put brackets around this, so that goes to 0. And we get the work done equals positive 1/2 k x max squared. So that equals the change in kinetic energy. Therefore, the change in spring energy is negative 1/2 k x max squared, right? Because the gain in kinetic energy equals the negative change in potential. So that's pretty cool. You've lost that much spring energy in going from there, so you've gained that much kinetic energy in getting to there. So pretty cool examples. And, you know, I probably should have looked at the graphs of doing this as well, right? So if you look at this from a graphical perspective here, gravity, right? Fg and y, the force of gravity versus the height here, well, close to the Earth, it's just a flat line. So, and I guess I actually, I guess you should have done it like this, right? Well, I guess if you know, negative mg, this would be interesting because this would be the change in potential energy of the object. Here, negative. That's interesting. So this is going to give you the area of that curve is whatever 0 h, right? Force is pulling down. This is going to give you the change in potential energy here. And it would be negative mgh, therefore delta k equals positive mgh. If you look at it for this one, now, you know, it's probably best to think of those force versus position graphs as magnitudes, right? For this one, spring force versus stretch distance, we usually draw it just going up linearly like this. So this gives 1/2 base times height. That'll give you your work done. I don't know. Positive and negative gets confusing when you look at these two graphs here. All right, so now let's look at a pure force position function. All right, so we could have some force, right, that increases as you move. So let's say this is our origin, right, in physical space. And as I move this way, the force gets bigger. So maybe there's maybe this is an electron floating over here, right? And this is a big positively charged plate, right? as you get closer to that, the force is going to increase. As the radius goes down, the force increases. So, I don't know. Just something pulling on it, so you get closer, the force gets bigger. So let's just make up a random force function here. Let's say it's 2x squared plus x, right? And I want to figure out the change, and we have some particle here. We have some object, right? It has some mass. Mass equals 0.10 kilograms. All right, I want to figure out the work done in moving that object from, a displacement of positive, delta x, we'll say is positive, I don't know, 20 centimeters or positive 0.2 meters. All right, so we're looking for the work done, or the change in kinetic energy, delta K equals what for a displacement from 0 meters to 0.20 meters. And then it really depends. Pretty much you're always going to want to make your object start at the position of 0 so that your limit on your integration is, just one-sided. All right, so the work done, or the change in kinetic energy, equals the integral of 2x squared plus x dx from 0 to 0.20 meters. All right, so the change in kinetic energy is 2x cubed over 3 plus, what did I say this was, plus x squared over 2, evaluated from 0 to 0.2. All right. Oh boy, now I'm going to need a calculator here. It's over in my other area here. I changed the location of my videoing area to try to get a little better light on the video. So 2 times 0.2 cubed, alright, divided by 3 plus 0.2 squared divided by 2 is about 0.025 joules of change in kinetic energy. So usually you have to be told what the initial velocity is as well. So V naught, I'll say, is 0 meters per second, right? So if that's a change in kinetic energy, and we started with no kinetic energy, K final, right, equals 0.025 joules equals 1/2 mv final squared. So this is just like what we were doing with work equals force times distance and setting that equal to the change in kinetic energy. However, now it's the integral of a force position function equals, and what would this graph look like, right? Oh, I don't know. If I take a look at force versus position here. So at x equals 0, we have 0. At x equals 1, we'd have like 3. So it's going to be like some curved function. So we're finding the area under the curve from 0 to 0.2 meters here. All right, so if I go farther here, it's going to get a lot more kinetic energy a lot quicker. So we're finding the area under the curve here from 0 to 0.2 meters. Anyhow, so if I said it's a 0.1 kilogram mass, all right, so 2 times 0.025 joules divided by 0.10 kilograms equals V final squared. All right, so this is going to be a pretty darn slow speed, which happens when you just make up numbers. 2 times 0.025 divided by 0.10, that gives me 0.5. Square root of 0.5 is 0.7. So V final was 0.71 meters per second. Pretty slow, but it's going to get exponentially faster, right? So that's the basic mechanics here, right? Now, this is kind of an interesting thing here. You may have recognized this already, and this is going to come into play on the next worksheet, but I'll give you a preview right now. So if we have a force versus position function, right? And it's curved, let's say. And the area under that gives me the work done, or change in kinetic energy. delta KE or delta K, right? When we had other functions, we took the area under the curve, we said that took us up a level, right? The antiderivative of this function brings us up to work. So what's interesting is this would be alter curve, not linear. This is, you know, if we take the antiderivative, we get up to kinetic energy versus position, or work versus position, right? So therefore, to get back down to here, it turns out the slope of kinetic energy position function or a work position function equals force. All right. Now, the slope of that, it means the rate of change of kinetic energy with respect to position equals force, or the rate of change of work with respect to position equals force, or the one we use most often, if it's, you know, kinetic energy and potential energy, right? Typically, what we're given is the potential energy function. All right, so it turns out that the negative derivative of potential energy gives us force. Right, and you can instantly check that out with gravitational potential energy. Right, use UG equals, let's call it mgy. Right, the derivative of that. So the derivative, negative derivative of mgy with respect to y equals negative mg equals fg. You can do the same thing with spring potential energy as well. Pretty interesting, but we'll come back to that on the next worksheet. All right, so the integral, and this brings up, you know, the negative sign here is confusing. So the integral of force versus position gives us work or change in kinetic energy, or the negative change in potential. The derivative of kinetic, or the negative derivative of potential energy, gives us force, and it goes back and forth. Back and forth, not back and forth. All right, I'm going to end this here, a little long-winded. Do your best on finishing up those force functions on this worksheet, and we'll talk to you later.